Today, we're going to be starting electron structure. So I just have an opening little joke. So here we have a photo, and it checks into a hotel, and the bellhop asks, "Can I help you with your luggage?" And it replies, "I don't have any. I'm traveling light." So this, in case you don't know, a photon is what we consider like a particle of light. So that's the joke. So anyway, so I want to go over one thing we did not go over the last unit with the atom are the how the atomics, what we know about the atom evolved over time. So early on, a lot of scientists just thought that the atom was indivisible. We now know that's not true. One thing that was discovered was that the atom did contain electrons. That was the first major discovery where we showed that there were particles within the atom. Rutherford came along and he discovered the nucleus. And one question that came up from Rutherford's model, where we had a nucleus in the center of the atom with a positive charge, and we had electrons that were orbiting that nucleus, and the electrons had negative charge. One major question was, why don't the electrons just barrel into the nucleus? Here, the electrons are rotating around the nucleus. Why don't they just get attracted to the nucleus and the atom itself collapse? So that was a big question. Okay, so around the time where Rutherford came up with this model, around 1911, there really wasn't any good scientific explanation for this. So this was something that scientists had questions about, and then they started exploring the atom further, and eventually they figured out what was going on. So we're going to go over how they would figure out something about something that you couldn't even see. We can't see atoms, so how do we explore what's going on inside an atom? Okay, so and also we have electrons that are moving so fast, they're moving close to the speed of light. How do you understand something, or how do you examine something that you can't see, and also something that's moving very, very fast? So the way we do that is by looking at how light interacts with matter, in this case, how light interacts with atoms. So before we get into this unit and understanding why electrons are arranged the way they are in atoms, how they're arranged in atoms, we're going to first review some information about light, because how light behaves when it interacts with atoms is critical to our understanding of the atom. Okay, so when we're talking about light, when we're looking at the light around us, the light that we can see, this is only one small fraction of the electromagnetic spectrum. So if you examine this slide here, and let me move this, what you'll see is that we have visible light in the very middle of the spectrum that we're examining here. At the low energy end, where the wavelengths are long, we have radio waves, we have our microwaves, we have our television channels, we have infrared radiation, which is heat. When you use night vision goggles, that's the energy that you're examining is infrared radiation. The higher energy part of the spectra, we have UV radiation that causes us to get tan and also can cause skin cancer. We have x-rays, so when we break our leg or break a finger or whatever and go get x-rays done, that's what they use to examine our bones. And then we have gamma radiation that can be used to treat cancer. So it has some good uses for it, and also can cause cancer, so it can also be dangerous. So all this is electromagnetic spectrum. And one thing I want you to notice is that the low energy end, the wavelengths are long. The high energy end, the wavelengths are short. One thing I want you to also notice is electromagnetic radiation is very unique. It can travel through a vacuum. That is why we can actually get heat and light from the sun. We have a vacuum out in space, basically, close to a vacuum. And if that weren't the case, we wouldn't get any energy from the sun, and our planet would be devoid of life. It would be extremely cold. So, sound needs matter to travel through. Electromagnetic radiation does not need matter to travel through. So, sound does not travel through space, but electromagnetic radiation does travel through space. So let's go to the next slide. So one thing I want to go over is the behavior of waves, because now we know that that light is a type of wave. So how do we know that? Some early scientists, including Newton, thought light was a particle. So it took some examination of light's behavior to eventually prove that light is a wave. So let's go over some of that proof that light is a wave. Okay, so one piece of evidence that we have used to show that the light is a wave is by the fact that light itself can be diffracted. So if you think about, like, if you go to a lake and you go sit on a dock and you look at the waves crashing or just moving against the dock, what you will see is that they will bend, they will get distorted as they move around that dock. We see the same thing with light. So if we see light moving around a corner, if we see light passing through a slit, what we would have expected if it behaved like a particle is that the light would just pass through that slit. We would see a slit, like a rectangle of light on the other side. Instead, what you notice here is as the light passes through the slit, the edges of those bands of light that have passed through the slit are a little bit fuzzy. They're not very sharp. And that's because the light is actually bending around that obstacle, around that slit. And this is what we call diffraction. So this light is actually spreading, because it's a wave, around an obstacle. So we see this when it goes through a single slit. We also see it when it moves around a straight edge. Okay, so these are just two pictures showing that diffraction of light. Another thing we see with light and we see with other types of waves is something called constructive interference. So if you have two sources of light and the light is a single wavelength, so here the red is showing that the light is a single wavelength of red light. If they are constructively interfering, that means that they're exactly in sync. All the crests and all the troughs are exactly lined up for each of the waves. What we see is that we get a more intense light that's produced from that constructive interference. That means the light will be brighter as a result. If we were to have constructive interference with sound, if you had two sources of sound and the sound were a single wavelength, a single pitch, the sound would end up being louder. So you would have louder sound. When we have brighter light, that's a more intense light. Louder sound is more intense sound wave. Likewise, if we have two sources of light and each source of light is a single wavelength, once again, we have two sources of red light. If they are destructively interfering, that means that the troughs are lined up with the crests for the two different waves. So here we have a trough lined up with the crest. What we see is that those two sources of light end up essentially canceling each other out, and we have a dark spot. We can also have this with sound. If we have two sound waves that are exactly just one wavelength, it means one pitch, and they destructively interfere, we would hear nothing. as a result. That would be a destructive interference. Yes, so the fact that we see constructive and destructive interference with light is just one piece of evidence that light does behave as a wave. Okay, so what I want to go over next, and I'm going to show you a picture of this, and then I found a really cool video, which I think will help you to understand this experiment, is there was a scientist who had the last name of Young, who did what is called a double slit experiment. So what we have here is to do this, to make it work, ideally, you would start with like a light source that had a single wavelength, like something from a laser. So we have a single wavelength of light. It's passing through a slit. That wave then is passing through two slits. And what we actually see is as the light passes through those two slits, it produces two new waves. They both have the same wavelength as the original light, but now they are constructively and destructively interfering with each other. And you get a pattern of dark and light bands from the constructive and destructive interference. Now, if light behaved like a particle, what you would expect would be that you would end up getting probably just after that first slit, you would just get like a line here of light hitting it. Since light is a particle, it would not be spreading out, because if it were a particle, it would not be behaving like a wave. So I want to show you a video of this to help you to better understand what someone would have expected if they thought that light behaved as a particle, and what they indeed saw, an explanation for it, um, since light behaves as a wave. So I'm going to bring up this video and I want you to watch it.
And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands.
Okay, so now we know that light behaves as a wave, and I want to go over some different properties of waves, just to give you some vocabulary that we will be referencing throughout this unit when we're talking about waves. So one property of a wave is the frequency of the wave. So on this slide, we have three different waves. This is visible light. It's going to be three different colors. So we think a look at the top one is red light in this case. We see that there's four of these waves. If you look, there's four crests or four troughs that are passing a certain point in 1 second. So we say that it has a frequency of 4 per second or 4 hertz. The second wave is orange light. We see that there's 12 crests or 12 troughs that are passing a certain point in 1 second. So we say the frequency in the second case is 12 hertz. The third one is purple light. We see here there's about 36 crests or 36 troughs that are passing a certain point in a second. So there's a frequency of 36 hertz. So this slide demonstrates what frequency is when we're talking about waves. And I want to also give you the symbol for frequency that you will see when we're working on equations, when we're doing problems with frequency. So let me just ink on this slide so you guys can see. And so if we look at the symbol for frequency is a Greek letter, and it looks like this. Looks like a V with kind of a curly Q at the right-hand side on the top. This is pronounced nu. This is frequency. The unit for frequency, so the units are, there's several different units you can use for frequency. One is 1 over seconds. This sometimes be written as seconds to the -1. This is referred to as hertz. And the abbreviation for hertz is Hz. So this is frequency. Now I want to go over a wave and just show you some other parts of the wave. So we have frequency. Another part of the wave is wavelength. So the green arrow there is representing wavelength. So this is the symbol for wavelength. This is lambda. This is another Greek letter, so it kind of looks like an upside down Y. The units for this is meters. Okay, now the top of the wave is the crest. The bottom of the wave is the trough. The black arrows on the slide represent the amplitude. So when we think about very bright light would have a large amplitude. Very dim light would have a very low amplitude. If we're thinking about sound, very loud sound would have a large amplitude. Very soft sound, whispering, would have very low amplitude. Now the blue dashed line in the middle is the origin. So those are just some different parts of the wave. Okay, now what I want to do is go over the equation that will relate the amplitude and the frequency of the light to the speed of light. So let's go to the next slide and go down here. Okay, so the equation that relates these is c, which is the speed of light, is equal to the wavelength, lambda, times the frequency, nu. So when we're talking about electromagnetic radiation, the speed of light is 3 × 10⁸ meters per second. Now, obviously, sound does not travel at that same speed. So if we were talking about sound, we would be using a different speed for the speed of sound. Okay, so I want you guys to write this equation down. And now we're going to work on a few problems that you're going to be seeing on the worksheets on Google Classroom.